Okay. Okay, so what I'm going to talk about today is some sort of weird data point, because on the one hand, I feel it has a lot of things in common with the sort of stuff that I've heard around here for the last 2 weeks, like reality is complicated, like real life systems are not as pretty as you hope they would be, things at scale pose new problems and these sort of things. On the other hand, the object that I'm looking at is actually very much a theory object, which makes certain things quite different. Like, I'm not trying to talk to ARM engineers or Facebook developers. I'm talking to people that, some of the people that actually built the thing that I'm trying to verify, and the ones that are helping me to verify it are actually the same people, which has certain benefits. But I hope it's an interesting thing to talk about. And so maybe what I want to talk about is kind of general efforts to look at some sort of realistic proof assistance and trying to certify as much as we can on them. Okay, so I guess most of you in the room probably have played with one of these things before in your life. And they're not as good as we would like them to be, but they're still quite useful for a range of things. But the thing that makes them usable, as for all things in real life, is that they're complicated and have, Isabelle Hall is maybe a slightly different data point, but for the kind of deep typed ones out there, they have all sorts of fancy type theoretic things. And basically, most of these things, all of these things are used one way or another in some sort of big complicated library in some sort of crucial way. So these are really features that we need. And there's more that people are, like on the type theory side, are working on and want to add in this thing, maybe making the whole thing even more complicated. And so we have the same sort of kind of problem of like, what are we doing and what's happening there? And since these things are supposed to be some sort of kind of very solid foundation, which a lot of other things can be built, if we don't know what we're doing already in our proof assistant, it's not a good sign for the whole rest of the ecosystem. So yeah, real proof assistants are complicated, which means it's both interesting and challenging to try to make sense of what we're doing. But then, we're formal method people, so we know how to make sense of these sort of complicated things. We have tools for this, so let's try to apply them to that. And so kind of the flagship project in this area is this MetaCoq project with this nice rooster logo. And so the goal is, kind of simple, is to talk about coq in coq and like say all sorts of things. There's a bunch of people in there. The names are not in the right order because I smartly edited the picture to make it fit on my slide. But there's a bunch of people, mostly, I think the main dev is Mathieu. Nicolas is quite involved as well, Theo and Yannick and me as well, and like kind of the crowd from France, mostly from Nantes. Now some of us emigrated in other places. But yeah, so it's kind of a large collaborative project. And there's a bunch of things in there. There's one aspect which was actually the origin of the project. I think Gregory developed that a long time ago on having this quoting and unquoting mechanism so that you can basically have a representation of things that happen in the kernel of coq inside of coq itself as like data types. You have a data type of terms and a data type of environments and contexts and universes and all of these sort of things. And you have coq commands to like take an actual coq program and then quote it into this data type and then unquote it back once you're happy with doing. So that was the original infrastructure, which I'm not going to talk that much about because it's not really, this bit is kind of the uncertified bit. But then on top of this thing, there's a bunch of more kind of theoretical things out there. So the first thing is that this thing is a bit too close to the actual coq kernel for our liking. So there's some sort of light translation to this slightly simplified system, pquick, which gets rid of like the fact that, for instance, here applications are NRE, which is very painful. There are some kind of cast nodes that are not very necessary for the theory here, things like that. So we have a translation to this slightly simpler calculus and proves that they're basically doing the same. So like this is type preserving both directions. And this is kind of our main object of study. That's where we do our meta theory. So we prove a bunch of nice properties on this. That's where we want to also have a certified type checker, although maybe it would actually make more sense to have it here. But for now, this is where it lives, because it needs all of the meta theory to actually work out. And then recently there's also been work, because another kind of big complicated piece of the Coq ecosystem is this extraction mechanism that takes a nice pure function in Coq or in here, and then spits out OCaml, and now there's a bunch of other backends. And so this is also a complicated thing and quite an important part of the whole like trusted story. And so there's also a certification effort on this thing to get down to this malfunction, which is not exactly OCaml, it's like something that Stephen Dolan designed as a kind of slightly higher level representation of one of the intermediate layer of the OCaml compiler for technical reasons I won't go into too much, but the point is that you can get guarantees on this extraction as well. And we also have formalized some of these things. Yes?
Does any part of that mechanism transport to like the reasoning about the translation done in VM compute or things like that?
So currently, in our certified type checker, we have one conversion machine, which is basically the basic one from the kernel. But I think one of the many directions it would be interesting to go into would be to try to certify something that looks like VM compute against, because here we have a specification of like the abstract conversion relations, like it's a transitive relation, symmetric, reflexive, all that. And so in principle, you could verify VM compute or something that looks like VM compute against the specification. This would be quite an interesting exercise. But for now, we only have the one kind of simple machine.
And all this stuff supports all the universes and all that stuff.
So I'll get back to the actual things that we have, I mean, in Peak we have crazy universe polymorphism, almost inductive types are basically as general as Cox. I think we don't have nested inductive types, but we have like mutual inductive with like prop and type stuff and co-inductive types. And so, I mean, the predicative calculus of universe polymorphic inductive constructions. So it's predicative because like we don't have the old impredicative set, which was a very complicated thing. So the CIC is calculus of inductive constructions, and the U is universe polymorphic. Yeah. Yes.
What does that give you that the template Coq doesn't already have?
This so actually it removes stuff. So it makes theory easier. So I think the main two things is that here we have a bunch of NRE constructions, like application that can take a list of arguments, and reasoning about this is very annoying, especially when you have dependent types all over the place. So here we have unary application. And the other thing is that in Coq you can have a cast node which kind of records typing information. And that's useful for like VM compute stuff and whatnot. If you want to carefully just say like, I want to know that this thing has this type with this precise evaluation machine. But this, from the point of view of the type theory, is just kind of information for the type checker, but it doesn't really participate in actually typing the thing. So what the translation does is it simply removes all of these cast nodes, and we show that this is a type preserving.
So on the one hand, it's kind of like an idealized code.
Yeah, it is slightly idealized, yes.
On the other hand, it's more expressive.
It is just as expressive, basically. Yes, yes. I mean, there are two kinds of universes in Coq: the old ones and the new ones. That's so whatever. But that's part of the real life, right? That's the whole point of looking at these things. Yes. Yes, it does. I mean, this thing is pretty faithful in all the gory details to what Coq actually does. There are a few things that we're missing yet, but it's complicated enough that we have actually, I mean, it forces us to think hard about some of the dirty places of Coq. Like so there are two props in Coq. There's the new one. So S prop and prop. So prop is compatible with propositional proof irrelevance and has restrictions, and it is the thing that gets erased at extraction. This is the old one. And then there is also S prop, which is definitionally proof irrelevant. And we do have S prop in our universes. We don't have definitional proof irrelevance yet. But that's also on the, I think we have a branch that does quite a bit of it, but it's not in the main repo yet. Yeah, exactly. Yes. Yeah. Yeah. Yeah.
Should the certified type checker work on that if and only if the original thing object?
So that's the goal. For now, we're still, I think there's like one killing missing feature, which is italos, especially for functions, which are used all over the place without you really noticing. And so it means that at the moment, we have type checked some kind of small Coq developments that don't really use it. But we're not yet able to type check big things. Like ideally, we'd want to type check ourselves, but we can't do that yet. Yes, because it's missing certain things that are in the actual kernel. Yeah. So it does not at the moment. Yes, yes. I'll explain why later on, but that's kind of a theory question, actually. We don't know how to do the theory with ITA. It is an important caveat. I think that's the biggest caveat we have at the moment. And I think ITA is less important maybe in the kind of the Coq ecosystem, but still this is the main thing that prevents us from taking big developments. Extraction, though, works very well. And like we can extract ourselves. So we can extract our, like extraction can extract itself. It can also extract the type checker. And so like the certified extraction that's there is actually, like the hope is to use it to replace the old extraction of Coq, which is uncertified and has a lot of wacky features. And it's really like on a good way there. Yeah.
Sorry, so when you say it's certified, you have a model of Dolan's malfunction?
Yeah. So there's an operational semantics for this, an operational semantics for this, and it's saying that for like first order functions, the two agree. For higher order functions are crazy and we don't try to do anything because like here you have effects and Coq kind of assumes things are not are pure. But for first order function, there's a theorem that's actually proven saying that the two agree.
So just to join dots inside my little head, this is new extraction which Thibault is not yet using because we don't quite believe it's right.
I think so, yes. Yeah. There's like, I mean, this is very recent. Like this extraction, I think, was PLDI this year. Or like, I mean, it's out there. It's been out there for a few months. And I mean, the PLDI paper is out there, but then there's all the engineering to actually kind of hook it into all the right places and so on is still kind of ongoing. No. There's two ways to do extraction. There's the old Letouze one, which has been around and slightly broken for a long time and opt magic everywhere. And this is the new one that is supposed to replace the old Letouze one, and which happens to be certified. But
it doesn't give you OCaml for.
No, it gives you OCaml compiled things and it gives you an interface file, so you can link it with other OCaml code, but you don't get OCaml source code. Well, the thing is that the type system of OCaml is incompatible with the type system of Coq. So either you have object magic everywhere and wacky things happening, or you accept that you generate code that is not well typed. And this is basically like one of the highest layer of the I think this is the first untyped layer of the OCaml compiler, basically. So the first thing where you can give something without object magic everywhere. That's a different conversation, and I mean, that's a trade-off. And I think the pragma here is to do like realizability style semantic typing, saying like, okay, you type check your thing in Coq. This gives you a type like syntactic type checking in Coq. You extract it, you get a semantic typing constraint on the OCaml code, and that's all you get. Anyway, so that's the picture. And I was not supposed to spend 15 minutes on there, but it's good. Okay, and so, I mean, there's like a big paper which is hopefully going to appear soon. It's on the internet, and it kind of tells the whole story kind of back to back. So it's a long thing, and if you want to like, and I just wrote an introduction for this, actually for the latest revision. This is like 5 pages of all the dirty things that are in Coq and kind of explaining what we have and what we don't, etc. So if you want to know exactly what's in there and what's not in there, the explanation is in this paper. Yeah, indeed. Hopefully we've done the last revision rounds and the next one is going to appear, but we'll see. Okay, so as I said, this is kind of smaller than what people here seem to typically do. Still, it's a real life thing. But the challenge is not really to specify it. I mean, the specification is non-trivial, but it's not too hard. The actual challenge is to prove that this thing has any good type theoretic properties. That's where the real difficulty lies. So just to show you, this is the whole inductive data type of terms. It's kind of a mouthful. It has 3 forms of variables because that's what Coq has. It has kind of a crazy thing for pattern matching with a bunch of things that are kind of hidden in these sub things, and it has like cofix points and so on, primitive values. So I mean, it's a non-trivial thing, but it's also like it fits on a slide. So yeah, and then yeah. So this is the Bruyne variable. This is a Bruyne kind of variable. This is a named variable for, so like there's some sort of locally nameless each thing happening. And this is meta variables with their substitution. And then we have, so let's, which is a real pain because now we have defined things everywhere in context and so on, which makes quite a change with simply typed lambda calculus and is big source of headaches. This is universes, and this is a monster, actually contains a lot of funky things. This is your like dependent typed language, like product types, lambda abstraction, global constants, inductive type, constructors for inductive types, pattern matching, projections for primitive records, fixed points and cofixed points, and primitive values. So now in Coq you can have primitive integers and strings and arrays, and they're all packed in there.
Did you think about the pros and cons of you can have more or less?
Yes.
Explicit information in the syntax?
Yeah. So the point is that the core of, I mean, this started as basically a copy of the OCaml data type of the kernel. So that was kind of a given, more or less. I mean, this is the Pickwick version, which is slightly simplified because I think the OCaml one has, so this cast nodes on top, app has a slightly different type. And I think prim is a bit more complicated in there. But this is basically a faithful copy of what's in the OCaml. And since at the end of the day, that's what we want to certify, this was more or less a given. Yeah.
You have a record type.
Yeah. Yes.
Record type, you can write recursion and also subtyping. Do you have subtyping?
We don't have subtyping for record types. We have just a tiny bit of subtyping, which is basically having to do with universes, and that's it. But I also have a different research line on actual subtyping for dependent types, which is on the theory side, but not in there yet. Maybe Arthur in 6 months will have more stories there, but for now it's not. Yeah.
You didn't make this exactly the implementation data type
Because that's what this translation is for. So this one has the data type, which is literally, I mean, copy pasting the OCaml thing in Coq, and so quoting, that's basically nothing. But this is the bit where we want to simplify things a little bit so that we can do theory. Yeah. But so the main reason this is simpler is we want to do theory on it and want it to be well suited for that. Yes. Yes.
That the construction of inductive types
Yeah.
is part of your
You know?
term syntax. Does
Yeah.
it mean that you have type checking rules for constructing inductive types in an arbitrary context?
No. So this inductive type here, there's a bunch of things, including a reference to a kernel, to a thing in a global environment.
Right.
So no, so we don't have local definitions of inductive types. This is basically a reference. I mean, I think we considered, in the end, we don't do it because that's not what the Coq kernel does, but I think it would be sensible to also just collapse these 3 things into just one kind of constant, and then certain constants happen to be constructors or inductive types and have slightly funkier things.
Plans to make first class.
No. Coq is crazy enough already. Okay, and so that's the terms. I mean, typing is a bit what you'd expect for the things that you'd expect. Like, I mean, for lambda, I mean, there's a bunch of things that are a bit more complicated. We have this global context, which is like all the things that you've ever defined in your life, like all the inductive types that were declared, all the previous definitions, and so on. So this is quite big and complicated. And we have this funky checker flags, which also kind of let you have some sort of modularity into like having certain knobs on and off. But apart from that, this is basically what you'd expect. Like a lambda has a dependent product type if whatever the body has a type in the extended context, and then the type is well timed. So that's, yeah. Yeah, sorry. So this is where this thing, this is just our notation for our judgment. So this is inductively defining, sorry. So this is inductively defining this typing judgment. And this is just notation for this judgment. So this is like literally typing sigma, gamma, this thing, T and B. Because there's a where thing here at the very end that tells you that, yeah. Yeah, sorry. Yes, I didn't include it. This is big, where? This is context extension. So this is living, like this is parenthetizer and the gamma and the whole thing. Yeah, it's another defined notation for context extension. Yeah, sorry. Yeah, so this is lambda. I mean, case is a bit more hairy. And again, there's things hidden in this fence. State conditions and branch typing. Sorry? Yeah, maybe. Yeah. But I mean, so this is kind of nasty, but also not that crazy. And I don't want to tell you what this is all doing, but it's there. Okay, so now the question is, there's some sort of catch, right? Because we can write some sort of minimalistic kernel for Coq and maybe a few thousands line of pure functional code. I mean, it's a non-trivial exercise, but if you know enough of these things, it's not that terrible. The problem in trying to prove anything about this is not about like kind of what sort of code this is. It's that actually the whole working of this kernel relies on a lot of invariance. And if you want to establish this invariance, you need to think about dependent types. And this is where things explode. So basically, to certify the kernel, you need to have done a lot of meta theory. And so actually, a significant part of MetaCoq is not in the actually proving properties of the actual function bit. That's kind of easy. The hard bit is in establishing all the meta theory we need to be able to do this proof. And similar things, if you want to prove that kind of the typical like PL meta theory thing, like progress and preservation and all these sort of things, you also end up in similar issues that actually like these things also need some sort of the similar sort of properties that you also need to establish the invariance in the kernel. And get back to what I'll get to what this is in a minute. But basically, the message is that yeah, meta theory is really necessary to get there.
So have you written down the assumptions the kernel makes, like progress and preservation could be axioms, and then you say, and then there could be a project that's like we're verifying the kernel against these axioms.
So I'm
a separate project.
So this is not something that we've done in MetaCoq, but I actually have another project I'm going to talk about later where I try to do exactly this. Okay. So I try to kind of make an interface like these are the black box properties I need from a meta theory, and if you give me these, I can certify the kernel. I can actually certify different implementations of conversion checking and so on. And I think this is the direction where I want to push this, is really kind of separate this is the meta theory we need from the kind of standard certification thing of like, how do we prove a function correct? And since this function is like pure functional code, mostly it's not so bad. Yes?
So the kernel is some piece of code.
Yes.
That checks
yeah.
some proof object.
Yeah.
With respect to the formalization.
Yes. Yeah. Yeah. So basically,
so, can you tell me what the certification claim is?
The certification claim is that the function we implement decides this relation. So we have a function which says yes or no. And if it says yes, then indeed this relation holds. And if it says no, then this relation cannot hold. And it terminates, which is a complicated bit as well.
Well, why didn't you just verify the object in this definition so that you didn't need to do two separate things?
What do you mean by two separate things?
Why did you have the typing derivation built into this so that the derivation is now in this definition and you don't have to actually certify it independently?
So the thing is that I mean, the main thing that the kernel actually does is deciding this conversion or definition inequality, whatever you want to call it, which is like have this two dependent types, which can contain arbitrary data, computation, and so on, and tell me whether they're the same. And the way this is described in theory is like this is the least equivalence relation that's a congruence that contains all of these base cases. And this is really not what the kernel is doing. Kernel is doing like evaluation and things like that. And so this is the main interesting bit in the equivalence. And you really don't want, I mean, you want to show to whatever in your user manual something, I have this relation which is an equivalence relation and all that. And you don't want to subject users to, oh, actually the operational behavior of this thing is like this, and then we reduce this thing in there and so on. Maybe it's relevant for people that care about efficiency of these things, for instance, like Gregory does. But like there's kind of a separation of concern there that we want to impose.
Computation going on.
Yeah. Yeah. Yeah, in some senses.
Declared type theory, syntax axiom, as it were. You can generate the provable judgments in it, and you want to prove that that's a decidable
yeah.
thing.
Yeah.
That doesn't decide it. So verifying that algorithm is correct is pretty much the same as proving that the judgments are decidable.
Yeah, in some sense, yes. Yeah.
Okay, you have much more control over the exact sequence if you care about it.
Yeah, and that's another theme that's another theme here, is that we really want to verify a particular known given algorithm and not just have an abstract proof of decidability in a constructive system, because that one I don't think we can extract to something that's actually reasonably runnable. No, so that's an important theme as well in these things, is that like a constructive proof of decidability is nice, but in practice it doesn't give you what you want if you want to actually run things. Okay.
That's all true, sorry.
Unless all, yeah, but then you don't even know what you're, okay. So I guess, okay, time is running, so I'm not going to do, but like we have a bunch of like theoretical properties. This is the big property. This is the one big thing that's non-trivial to show, is that your types are injective, and that like you can't have, like if you have some sort of no confusion principle. This is the key property. People like in theory land, they say like, oh, the important thing is normalization. If I want to certify my kernel, progress and preservation, all of these things, these are the properties that I want. And because this allows you to kind of know that the types classify things in the way they should, so that this is telling you that a lambda cannot have type nat, for instance, things like this. So it's a very key property. And the way we obtain this as MetaCoq is by showing some sort of confluence properties. So we characterize this thing as, so we show that this thing is equivalent to reducing and then having this funky, slightly very structural subtyping relation. And by showing that these two things agree, it's kind of reasonable to show this injectivity for the confluency bit, and so we get it from for the other one.
I mean, you may well move later on to a funkier type theory.
Yes.
Which that probably just doesn't hold.
Exactly. So this is the big promise, that this strategy is very hardwiring the fact that our definitional equality is basically evaluation plus a teeny tiny bit of thing that is vague, like mostly structural. And indeed, it doesn't play well with the eta laws. It doesn't really play well with strict propositions. And so that's what I was saying. There's a theory happening there, is that like this whole proof structure is very dependent on this. And I don't know how to do similar things for the more interesting definition equality, in particular what Coq does at the moment. I don't know how to extend this story there. Okay, and then from that you get a bunch of things. You get the typical PL thing, progress and preservation, if you care about that. And then, and I'm going to talk about normalization in a second, but if you assume or prove normalization, so the fact that this, this reduction relation terminates, then you can get a bunch of things that are also nice in theory, in particular consistency, that you cannot prove false, which is nice. Also tells you that there's some Gödel thing happening here. And so that's a Gödel incompleteness thing happening. And this is the second problem here, which is kind of a source of, yeah.
I'm going to Field normalization.
This is the next slide. Okay, so this tells you that there must be a catch somewhere because Gödel second incompleteness theorem, blah, blah, blah. So if you start saying these things, you have Gödel looking at you with this very disappointed face. And so actually, what we do, well, yeah, who knows? But so yeah, so that's another difficulty here is that we're really kind of playing with Gödel incompleteness. We know it's there, and we know we cannot possibly avoid it, so we have to kind of find ways. So our way at the moment is very crude. We just assume that this normalization property holds. And note that all these other properties, like all of this, and that doesn't depend on normalization. So still we get a lot of mileage without assuming it. But then if you want to get the kind of the last bit and know that our type checker terminates, we kind of need that. So we axiomatize it. So in practice, we just have this big axiom normalization saying like, well, every well-typed term is accessible for this reduction relation. And actually, it's a slightly more complicated story because so in Coq, you can only in principle define fixed points that are in some sort of sense structurally recursive. And there's this bit called the guard, which is the part that's checking it. And because the guard only exists for normalization, instead of having one precise given guard, we just assume that we are given one and that it has a bunch of properties. Like it's, for instance, this is saying that the guard is stable under reduction. I think there's also things that are stable under substitution, these sort of things. And assuming that there exists such a guard and that normalization holds, we get all the things we need. So that's all that we have to assume, but we have to assume that to make Gödel happy. Okay, and then once we have that, we can finally get back to our kernel question. So one direction is the soundless one, which is quite easy, really. So like if the kernel answers yes, then it has indeed been able to construct a typing derivation. And this is not very hard because like as the kernel goes, you just record all of the thing it checks, and at the end of the day, just assemble all of them, and you have built a typing derivation, and you're happy. The difficult thing is the other direction. So showing that the kernel never misses such a derivation. And for this, we actually have to kind of factor things out. We have this bidirectional presentation in the middle, which is, again, a big inductive predicate, but is much closer to the structure of the actual implementation. And then we show in theory land that these two predicates agree. And then it's relatively easy to show that the actual implementation satisfies this predicate because they basically have the same structure. So this is kind of a nice separation of concerns. And this is also useful for other things. Like there are a bunch of properties that are much easier to show on this side and on this side. And so it's also nice for theory land. But it's definitely kind of necessary if you want to get this completeness property.
This kernel
yeah.
is PCUIC kernel, not the actual kernel in the template, right?
No. This is a kernel for pquick. Yes. Yeah. And this is like written using equations and like the usual functional programming thing for Coq. The fun thing here, though, is that even though this kernel is not, I mean, it's close to what Coq's doing. It's not exactly the same one. Still, it's close enough that we were able to realize things. So when, I mean, there was a very bright, like, happy and joyous PhD student, and I started working on this, and deep down in the proof and like the case for pattern matching, there was something fishy with the universes. So I sat for a while, and then I really thought it was something fishy. So I went up to Mathieu and said, like, hey, I think there's something fishy with the universes. And actually, 2 hours later, there was this bug on the actual Coq kernel. So this is like the issue of the like genuine Coq/Coq repo, whatever, saying like, well, actually, we found a bug there. And so, I mean, even though this thing has no like formal relationship to what's actually happening in a kernel of Coq, it's close enough that by looking very hard at it, we can find things in a real thing. So it was basically the combination of universes, like the like universe polymorphism for inductive types and pattern matching. And it was a point where you really should be comparing contexts for subtyping, and you were comparing them for equality, basically. I mean, so it was a conceptual error, right? The code was just not doing the right thing. So it was not like we forgot substitution somewhere or something. It was just like a conceptual mistake. And once we found it, the patch that fixed this one, like kind of the hot patch, was relatively straightforward. There's a longer story that I'll tell a bit later, but I mean, finding the bug was the hard bit. And so, okay, oh no, so it's actually there. So the hotfix was easy, but actually the whole reason why this was able to kind of appear was that the way pattern matching was represented was really terrible. And there had been PRs and issues and whatnot and discussions in the Coq devs for a long time saying like we should really get rid of this terrible representation, and nobody really had the willpower to do it. And I think once we found an error that was basically like that could kind of go through because the design was kind of terrible, I think this was enough of a push to actually make this redesign happen. And so it happened basically in parallel in Coq and in MetaCoq, and I was able to finish my proof.
So that's nothing to do with Mathias' equation?
No, this is lower down. So this is lower down. This is pattern matching in a kernel. So basically, what was happening is that due to very old historical reasons, binders in pattern matching were still represented using lambdas and product types. And so there was some sort of weird ad hoc code that was taking something that was supposed to be a big pi and then something, and then extracting the context and the something, and then comparing things in some sort of weird way. But there was a lot of like weird hacky code around this. And so this is where the kind of the mistake happened. And so now we got rid of all of this and things are represented as normal binders and not using overloading lambdas and product types. Yeah, so this is vaguely useful. Okay, and so the last thing that I'm not going to talk about too much because honestly I was not really involved in it directly, but we also have the certified extraction. So basically, so the picture is a bit not very colorful, but so pquick is here. So this is kind of the part of the picture you had before. So you start with the Coq thing that you write, that's parsed and type checked in OCaml, then you quote it to pquick. And then we have this fancy thing called lambda box, which is basically the same as pquick, but where all proofs are erased. So you remove all the proof content that's not supposed to contribute to your programs. So that's erasure here, and then you do a bunch of optimization passes on this thing. And then once you're happy with your optimization, you compile it down to this malfunction language, the thing from Stephen Dolan. And from that, you get these OCaml things. Yes, it's still very close to, it's basically pquick with an extra constructor for erased content. And then everything that looked like a proposition just get mapped to this erased content, which is this box thing. So it's like, we don't care about this thing anymore. And then all of these optimization passes about kind of removing all of the bookkeeping that was useful when you had proofs, but is not necessary anymore once you've removed them. That's most of what's happening here.
Is this infrastructure the same as what's used in CertiCoq?
So CertiCoq, I think, hooks into here. So the other good thing is that I think there's also a Bassfitters has other backends for this. So kind of the plan is that this whole part can be shared by everybody who wants to compile Coq. And then if you want to compile Coq to your favorite language, you just hook into there, and instead of going to malfunction, you go to C, or you go to whatever. And CertiCoq is, I think, compiling from here to ComCert. Yeah, that's the plan. Yes, and this is all proven to preserve semantics, right? So if you have something, so the general thing is like operational semantics. So if you have something that gives you a first order value here, you get the same first order value here at the end of the day. And there's also a paper, I think it was, is it written here? Yeah, it's PLDI this year. If you want to read more about this. Okay, so we have now this fully certified, I mean, almost fully certified because of normalization, but like whatever kernel, we can extract it using, I mean, the whole point of this was we wanted to be able to extract our kernel and extraction, and this works. So we can actually run our own extracted kernel, which is quite nice, and was quite a headache, I think. For a few weeks, they spent a lot of time understanding what was going wrong with malfunction. Okay, so, but like there's still a bunch of things that we're not really happy about. So there's this axiomatized normalization thing. In particular, the guard is this kind of very black boxy thing in Coq and one of the probably weirdest corner of Coq. But then by axiomatizing normalization, we have no way of checking that the guard actually does its job, which is quite unsatisfying. I think for Andy and the semanticists in the room, we're still using untyped conversion, which is the thing from 20th century. Okay, so this is the thing for the 20th century, because this is the only thing where we know how to prove all these injectivity properties and so on without having to set up a logical relation. But we would really like to move away from it, in particular because this is what prevents us from having these eta rules, which are probably the main blocker now to type check big Coq developments. We're missing a few other features of Coq. This like template polymorphism is a very terrible ad hoc hack that should go away and be replaced by a much nicer one, which is sort polymorphism. And hopefully once this is done, probably we'll have it in MetaCoq at the same time. I forgot to write strict propositions there. It's on the branch in MetaCoq has some similar issues to eta rules, although it's a bit more tame. And hopefully we can get it at some point. And the last kind of crazy thing are modules, which are very weird in Coq. They're kind of generative, but also not really. And especially functors are quite a mess. So it would be nice to have a good story for this. And hopefully maybe by looking at them in MetaCoq, we can kind of clean up the story there as well.
Completely different level. Modules exist at a completely different level.
They are in the kernel. Modules and functors are in the kernel.
All of the theory you've done is on basically the expression language. Modules don't sit inside that.
Well, they do sit in the, I think, so, or I shouldn't have done that. So we have this global environment, which is currently basically flat. It's like just a big list of declarations. And I think this is where the whole module system would sit. So instead of having a big list of like a name declaring a new constant and a name declaring an inductive type and so on, we'd probably need to have some sort of more module structure there.
But your proofs are all like your proofs justify things like alpha renaming. So the structure of that doesn't matter as a proof? Or?
It doesn't matter, but I think the point is that typically, so modules themselves would probably be not too hard. The funky bit is functors. Because functors are basically, you have kind of this kind of global environment parameterized by a bunch of things. And then you want to know that when you instantiate this extra global environment, you can still type check things after the instantiation. So, but I think this in some senses is at a different level, I agree. It's not at the level of the kind of the term calculus, but rather at the level of the whole environment. But still, it's something that is in the kernel of Coq and that we would be able to talk about in MetaCoq in a reasonable way, and it's probably necessary to do it there. Or to change the module system of Coq.
So the soundness group would basically say that you can instantiate all functors appropriately and
yeah.
use a Coq program that does not use
yeah, I think something like that. So probably like if you have a functor and you type check the functor with its abstract parameters, and then you instantiate the functor, this is type preserving. Something like this, I think, would be the sort of theorem would be after. Yeah. And maybe we can also just remove them and sort of translating them away and translating functors away and so on. That would also be another option. But this is not currently what the kernel is doing. So like if you want to faithfully model what's happening there, then yeah. Okay. And I don't know how am I on time? Okay, I'm almost over. So this is the kind of my paid project since I'm in Cambridge, basically, is this kind of much more timer thing where we can actually do all the crazy things. So MetaCoq is somewhere out there. So like this, like quite expressive, trying to do as many properties as we can, but also this kind of this normalization gap. And the second project sits somewhere in there. So it's like a simpler system, but trying to go all the way. And okay, it's not really rendered well here, but the point is that we don't want to assume anything in the middle. So we really want to go all the way there axiom-free, which is a different challenge. So I'm not going to tell too much about it and like time and stuff, but so it's an even smaller system and it's really not real life anymore, but the proofs are even fancier. So I think in total, kind of the level of miserability is kind of the same. So we've traded real life for complicated proofs. It's a different quality of miserable, but we're still miserable. Yeah, and I'm not going to tell more about it here, but like this, I'm around. So if you want to chat a bit more about what's happening here, we can do it. But in particular, one of the things that I'm currently kind of wrapping up on top of this project is this, what I was saying earlier, of trying to separate clearly the sort of big properties that we need. So here we have a fancy logical relation, which is the fancier proof. But kind of the goal is to have a clear interface of what we need this logical relation to give us in sort of black boxy way, so that we can go on our way and like do our certified type checker and conversion checker and so on. So in some sort of sense, there's also some sort of sandbox-y thing to probe ideas that hopefully one day will make it into the big scary bit. But it's much easier to probe them at this level. Okay, and I guess the whole point of this workshop is to try to have some sort of lessons learned. So I'll try to do a little bit of that, and now it's going to devolve into bullet points because, yes. But okay, so on the MetaCoq side, it's doable, and it's not, I mean, it was a lot of work, but it was not that horrible. I don't know if it's a dedication to the people of Coq that trying to keep their kernel vaguely manageable over the decades, or what made it possible, but like it's reasonable.
So,
yeah.
Cool. Is there any particular reason why it's doable now rather than 20 years ago and maintained ever since?
So I think part of it was just that enough critical mass got interested in a thing and kind of gave it the start. I think part of it is that the tools are much better than they used to be 20 years ago. Like, I mean, there was a project at the, I think, the very end of the 90s by Bruno Barras. It was already called Coq and Coq and was doing all sorts of things there. I mean, it was kind of frightening because it was still the time of set theory. So it was like proof of normalization was going through a set theoretic model to prove normalization was very frightening. But at the end of the day, it didn't really have inductive types, which are the big scary monster there. And part of that is that if you look at the level of proofs and like the infrastructure that they were using, I think it wouldn't really have scaled to the sort of things that we have in MetaCoq because it was just too complicated. So the tools are miserable still, but they're much less miserable than they were 20 years ago, I think. There's still a long way to go, but yeah, I think it's mostly some sort of tuning thing and some sort of like critical mass. Yeah. That would be my main explanation. Yeah. Better tactics, better ID, better like more speed, more everything. Equations, which we use a lot to define all our fancy functions, which didn't exist at the time, so you don't have to write like Galena codes, looking at it in the eye with fancy pattern matching and inductive types, whatnot. Well, I don't think, this one was a port of an AGDA project, and I'm really happy I redid it in Coq, because even with my very low-level style of proof, I'm still very happy I have tactics. And I think my life was much less miserable than that of Andreas Abel and all the others that worked on the AGDA side. And I think Nicolas Tabarot, who worked on both sides, I think now decided that he'll never going to work on the AGDA side anymore, and that if he has to do anything again, he'll do it on the Coq side. So, yeah, maybe. Yeah. That
he describes not possible. Well, it's
no.
a nested index inductive type, and it doesn't really handle those in the kernel yet.
Yeah. So we even found a bug in Coq, so it's apparently vaguely useful to do the proofs and not just have the specification, because I don't think we would have seen any of that. I mean, that thing really appeared when we, and like when we found that bug, the people had been already doing the meta theory in MetaCoq for 2 or 3 years. So like it was really about like looking hard at this specific thing that we actually found the issue. So it's apparently useful. And I guess the nice thing is that it's slowly starting to kind of drive, or at least be a part of the general design of the kernel, the evolution of the kernel. And I guess this is helped by the fact that the two basically have, the Coq project and MetaCoq basically have the same lead developer, which is very helpful in this sort of cases, because you can just kind of change hats. But there are also people on the Coq side that are not directly part of MetaCoq, but still understand enough to kind of look at what's happening there, and vice versa. Like I've never touched the Coq kernel, but I understand quite well what's happening there, and I can have discussions on this because I know what's happening here. So I think in general, it's kind of a good place to be to kind of further the development of the thing. And there's a long list of bad. This is still very much heroic. I think we had the discussion for a while about like kind of how we can go from this sort of heroic projects to actually making this manageable. And like the pattern matching change, basically Mathieu spent a year. I mean, so we have the joke in the MetaCoq world that I think the bug was found somewhere in like October or something. And Mathieu said, oh, I'm going to change pattern matching. It's going to be ready for Christmas. And it was ready for Christmas the next year. So now in MetaCoq, our deadline is always Christmas, unspecified year. But yeah, so, and this was for pattern matching, but at some point, I think Nicola had a similar kind of big refactoring thing where he wanted to kind of factor out the representation of this global environment because you can't have a big list if you want to actually execute something because it's just too naive a data structure. So he tried to factor out the kind of the abstract representation that we use in proofs from the actual way this is concretely implemented. And so he just had to factor out a bunch of like type classes and stuff in all the code, and it was also terrible to do. So in general, there's still a lot of like heroism happening in this sort of project, sadly. None of us really are proof engineers, and that shows. There's like very little automation. We're using basically all features of Coq because we have the Coq devs, so they know all about Coq. They can use all of the features in a way that's not really thought out and not really well working together. So there's also a lot of issues there. And so generally, like, I don't know how much it would help, but there's definitely a lot of things to be said about doing these things kind of rigorously. And ideally from the start, because now I think retrofitting some of this in there would be a very hard task. But yeah. Another issue, which is kind of the reason actually why I ended up doing this kind of side project, was that it's very difficult to experiment. Like sometimes we want to try a new theory, a new idea, try a new proof and so on. And you really want to do it on kind of a simple case. And you really don't want to be proving it for pattern matching right away because maybe the thing is just wrong. And we can't really do that in MetaCoq. And it would be, I would really, really like to be able to kind of turn off and on certain parts of the language to kind of try things out. And currently we basically have no way to do that. And it's also like, I mean, the way I got into MetaCoq actually before that, I was trying to do gradual types for dependent type systems. And at some point I thought, we have this kind of nice formalization of a dependent type theory. Maybe I should try to do some of my pen and paper stuff in there. And I spent quite a bit of the COVID lockdown trying to do that alone in my room. And after a few months, I decided this was not the way to go because, again, like MetaCoq is too big and scary, and it's not really a good place to experiment with things. So I don't know if this sort of thing appears in other places, but there's definitely a pain point for us there. And kind of the last question is like, we're almost there, but not quite. And it's not entirely how hard this kind of last yard is going to be. Part of it is, I think modules, for instance, is mostly kind of sitting down and thinking hard about modules, but like there's no real theoretical difficulty, probably, mostly, hopefully, I don't know. But for like untyped conversion, Italos, for instance, clearly there's a theory question going on. And again, it's also linked to like the difficulty to experiment there. And it's not entirely clear even what the theory of that thing should be, but like, I guess we have to retreat into theory land before being able to jump that fence. And on the other side, so one of the things that we tried to do in the second project was to use as much of the kind of tooling that's out there. So we use this autosubs plugin for like all sorts of things linked to syntax and generating automatically substitution, all sorts of substitution lemmas and so on. It's useful. It's not as good as it could be. We're trying to kind of experiment with this library for defining partial functions and manipulating potentially non-terminating things and so on in some sort of fancy way using like a free recursion monad and so on, which is quite nice. But again, it's not really as polished as we would hope. So it's also kind of painful. There's a lot of fancy induction stuff happening all over the place. I actually wrote some fancy MetaCoq, like on the quoting side to do fancy manipulation of induction principles to generate new fancier induction principles and so on. And there's also the typical sort of things that we have to do in this sort of space. And there's not much support for these things around. So yeah, I think generally there's a lot of TL meta theory tooling that could be better, that we would benefit from. Catherine. Yeah, yeah. Yeah, I mean, I went to Scotland to talk with her already, and there's a question of also manpower here, like in many things. But I think, I mean, part of the problem with the so we're using this OCaml implementation because that's the one that's easy to install with OPAM. So very dumb reasons, but that thing. And the problem is that this thing was written by a student who was able to do the technical bit of kind of generating all of the substitution lemma and have them type checked and so on. But I don't think that student had a lot of experience with actually doing proofs. And so there's like the infrastructure kind of around these lemmas, like the rewriting automation and the notation stuff and all that is terrible, which means that we basically have to do our own on our side. But then I think like there's a like paper cuts, I guess, is part of the problem of AutoSoft. Like it could just prove the exact same thing, but have a better interface and like infrastructure, and it would make the whole thing just so much better.
That piece of OCaml code that generates something.
Yeah, so you give it a description of your syntax, and then it generates the ASC, the substitution and renaming functions, and all the lemmas on these. So like all the equations. Well, I don't mind because I mean it's generating the proofs as well. So like you just, I mean, so what we have is that we just have this big. I can actually show it to you maybe. Where is it? So we just have this kind of big crazy file that has all of these proofs, and all of this is auto-generated. So this is the fast thing. Like maybe it's a bit too small. Okay, so this is our syntax. So this is what we feed into the tool. And the output is this very big scalar file. So the first thing it does is define the inductive type, and then it defines somewhere substitution. Okay, so this is the definition of renaming. There's a definition of substitution there. And then there's like 1,000 lines of just all sorts of equalities between these things. And I mean, this is all checked by Coq at the end of the day. So I don't really mind on which side it sits. I mean, maybe it would be better to have it in Coq. I don't know. The fact that it's in OCaml is nice because it's at least we can kind of have the right requirement, and it's easy for building things and so on. But whether this should actually be programmed in Coq or in MetaCoq or in another LTAC or something or an external tool.
You see, if you did, because it seems to be almost inevitable that it never quite does exactly the thing that you want, and you want to change it.
Yeah. So one of the things is that I think the other advantage of the OCaml version is that it hooks into some of the Coq internals. So it looks like it's dumping syntax, but internally it's also talking with the Coq internal. So it's not completely a separate thing. Yeah, kind of. But I think there was an attempt at some point to re-implement some of these things in MetaCoq, the programming language, like the quoting mechanism. That didn't really go through. So I don't know what the right place to build these things is. What I know is that I want them.
In principle, it might be good to have the executable part of this, OCaml, in order to build things that are going to run for PL, not necessarily for MetaCoq, but
Yep.
other things you use AutoSoft for.
Yeah.
Building actual bits of implementation.
Yeah.
Good argument being stupid about it.
Yeah. But I mean, kind of the thing about Coq is that like you can run things. It's maybe not as good as if you had done it yourself, but like for extraction, you can get reasonable things. Maybe, I don't know. I mean, yeah, no, you don't think so?
I listen to people in the FS corridor.
Yeah. So I mean, I think there's two different things. I think extracting a constructive proof of something is a terrible idea. That doesn't work. Actually writing, I mean, if your program you want to write is some sort of pure functional program, actually writing it in Coq and then extracting is not entirely bad. It has some badnesses. It has some badnesses, but like, it is to balance with the fact that, for instance, like one of the problems with AutoSoft is that for a while we were using AutoSoft for Coq 8.13, so I had a switch of Coq with like I had the no-pam switch with Coq 8.13 so that I could run auto subs because it was talking to Coq in a way that was like not. So there's also a question of like, the good thing of having this sort of tooling kind of more integrated into the proof assistant is that it's the proof assistance people's job to like prevent bit rotting, which is very useful. So it's in here. And I think like for auto subs, we actually paid the price of pulling it from 8.13 to 8.20 and then put it in the place where it's the Cox people's job to update it, and now it's their problem, not ours. And this is a very comfortable thing to do. For some of us, yeah. No, but the point is that I think, I mean, the changes we had to make at the end of the day to port it were kind of trivial. The problem is that it took us days to understand in the Coq code base what was happening because we're not Coq devs. And I think for them, when they make a change in Coq master, it's very easy to like change the name of the function in the right place. So like we're giving some of our work to them, but I think that work for them is infinitesimally smaller than the same work would have been for us. And then hopefully maybe someday I'll know enough about Coq that I can do it on the Coq side, who knows, but yeah. So there's that. So yeah, so I was saying like meta theory, I want to kind of keep these two problems as separate as possible. And ideally, I mean, on the certification bit, I think there's like interesting questions, like all of these things we've certified for now are very toy-ish. And it would be very nice to look at things like VM computer, like the fancy, efficient, but also highly optimized like evaluation engines or these sort of things, which are really certification problems and not that much meta theory problems. And I think now, if we have this kind of nice separation, we could attack these sort of problems in a sensible way. But we kind of need this separation between them. And the last one is, I think, a quote of Derek Dreyer quoting Peter Sewell. It's like this: there must be a better way. This is the story of Iris, saying like, oh, like for 10 years we did this step index thing and it was really terrible and very annoying. And we have some sort of similar thing in our logic relation stuff, where we're doing partial equivalence relation by hand, and we are doing pre-sheaf function spaces by hand, so with like a quantification of a weakenings all over the place. And this gets very messy very fast. But actually, this is supposed to be kind of a nice model of type theory. So in principle, this could have some sort of dedicated logic on top of it to make our lives kind of much nicer and hide the issues. And I don't know whether there's any chance of doing some sort of Iris-style thing for that. Would be fun. The theory people have all of these fancy, complicated words that they say this is the theory way, the right theory way of doing these sort of business. But this is the support for these sort of things in proof assistance at the moment is not ideal. Agda can do some of that, but Agda can't do other things, and the other proof assistants basically cannot do that. But maybe this is the way, I don't know. This is at least the theory land answer is this. And then yes, this question of modularity and being able, I'd really like to be able to maybe even kind of do these sort of projects in some sort of logic programming way, but I say like, oh, okay, I have this like 5 typing rules here and these other 5 typing rules here and these other 5 here, and then I do the proof for these 5, and then I can import the others, and then I have proof obligations for these 5 others, and like this sort of very modular way of kind of importing things and kind of composing things together would be very nice and very useful. And like I think most of the proofs that we do there are kind of very structural inductions and so on, so it wouldn't be too hard to do these sort of things, but it would be very helpful. And I think that's mostly it for me. Thank you. Yes?
You mentioned about subtyping and co-induction in the first slide.
Yeah.
We are using a lot of taco, taco library for co-induction.
Yeah.
Because this is really the part, when mechanizing session types.
Mm-hmm.
And everything is related with subtyping, co-induction.
Uh-huh.
We didn't do record type subtyping, so it's a bit disappointed. But it's quite a lot of work using the taco library and how it co-induction.
So co-induction is slightly weird in Coq because as for universes and as for props, there are two co-inductions in Coq. There's the old broken one, which is the positive one, which is from the 90s and has been known since the beginning to break good type theoretic properties, in particular subject reduction. And then there's the new one, which is the negative one, which is kind of recursive records, which doesn't break subject reduction, but proves less things. So I think some people have strong opinions on one or the other. And there's a complicated story here that like the positive co-induction is present in some bits of MetaCoq, but not all, because for instance, the subject reduction proof kind of forbids this positive co-inductive types because we cannot prove subject reduction for them. But in general, there's not that much things there. I mean, co-induction is not too crazy a thing there. I mean, it's not crazier than inductive types in some sense. But I think part of the reason is because Coq's support for co-induction is pretty bad. So, I mean, on a long list of things that maybe would be interesting to look at is whether we can make co-induction better, and maybe like as for other extensions, maybe like if we want to extend fancy things in the kernel, then maybe also kind of use MetaCoq as again as kind of a safety net to make sure that the new fancy things that we've done are not, I mean, keep all the good meta theory. Yeah, but yeah. Yeah. Yeah.